Hello again and welcome. During my last video I showed making an oscillator on a section of breadboard, and that oscillator ran up to 6.3 gigahertz. The fastest oscilloscope that I own is the LeCroy Wavemaster. That's an 8500A. That has an analog bandwidth of 5 gigahertz. I also have an old LeCroy 7200A that was in that video. That has an analog bandwidth of 4 gigahertz. My first oscilloscope was made by Dumont. It was something that somebody had given to me. I don't remember the bandwidth on that, but maybe it was a megahertz at tops. I ended up building this box. This is essentially a digitizer. There's an analog input, an analog output, a trigger in and a trigger out. So I can connect this up to my circuit, and I can single shot capture a waveform, and then I can play it back repetitively. So on an analog scope, it basically makes it look like a digital scope. The nice thing about this is the output stage, I want to say, could output more than an amp. So you could actually use this to drive a motor, for example. If I showed you inside of this thing, I'm sure I've got some pictures of it, but there's a circuit board that sits in the top of this, and that's all loaded with DIP ICs, and then it's completely wire wrapped. On the side you can see it has a printer port. That's actually to drive a printer. And then the serial port. This allows me to offload the data to a PC. So let's say you had a 1 megahertz analog scope and you were going to try to increase the bandwidth. If you didn't want to lose any information, one way that you could do that is you could use a digitizer like this, capture the data at say 10 megahertz, and then play it back. It's something that the scope could handle. So again, we'd have some kind of an output trigger that would drive the scope's input trigger, and that would be delayed, and that would allow us to basically index through that captured waveform. So if we had a 2-channel digital oscilloscope, and let's say we want to increase the sampling rate of it. Let's say here's the waveform that we want to capture, and let's say normally the scope samples at this rate, and let's say we wanted to double that. What I could do is combine these 2 channels, and I could offset them by half the time, and then I could stitch them back together, and basically that would double the sample rate. So the old LeCroy 7200 supports this mode. There's an external adapter. This is what it looks like. So this is just a delay line, and it's causing, in this case, a 500 picosecond delay between the 2 channels. And then these dip switches add different lengths to that delay line. There's a resistor built up into the connectors, and that tells the oscilloscope that this is attached, and that'll cause the software to stitch the waveforms back together. And you can see there's a little cable here with an SMA. This goes to your load that you're trying to measure. When I first wanted to play with this, these were not available, and so I ended up making one. There's essentially a resistive splitter, and then I used a section of coax, about 3 inches, to give me that 500 picoseconds, and that was basically all there is to it. So on mine there's no adjustments, it's mechanically fixed. Now on newer oscilloscopes, like this LeCroy 64XI, this has the interleaving mode built into it. So this scope will normally capture at 5 gigasamples per second, and that's on all 4 channels. This scope has hardware to interleave the first 2 and the last 2 channels. Basically what it allows you to do then is use channel 2 and 3 as your inputs and double the sample rate from 5 gigasamples to 10 gigasamples. My LeCroy Wavemaster does the same thing. That oscilloscope can capture at 10 gigasamples per second with all 4 channels, or it can do 20 gigasamples with 2 channels. Now again, these oscilloscopes also support wrist mode. Of course, that requires a repetitive waveform. The problem with the wrist mode is, of course, it's random interleave. Over some number of cycles, you can actually rebuild the shape of the waveform. But if I had a transient, for example, that we're trying to capture, that type of mode is not going to allow you to view that. I was using this 64XI to first look at the oscillator. Again, this has a 600 megahertz bandwidth, and we were looking at waveforms all the way up to 1.2 gigahertz. That's going to reduce the displayed amplitude of the waveform. And as we went up in frequency, the signal and noise ratio got so bad that essentially the scope could no longer trigger on it, and all we were seeing was noise. I think the oscilloscope was actually displaying over 23 gigahertz at one point, and obviously that's not real. So let's say we had this same type of oscilloscope, and we wanted to combine these 2 channels, not to increase the sample rate, but to increase the bandwidth of the scope. So again, let's just say that this is a 10 megahertz scope. Each of these channels have an analog bandwidth of 10 megahertz, but what we want to do is double that to give us a 20 megahertz bandwidth. So before we get into this, I was going to explain how this has a lot to do with radio, and I was going to mention this ARRL handbook. I pulled this out of the shelf, and when I grabbed it, and I felt this big lump, and I looked down in there, and what do you think I saw? You know what this is? That's the knob off of our scope. It's not the first time that these knobs have fallen off, but I'm glad it didn't become a cat toy. It's funny how it ended up in the book cover though. So anyway, getting back to our video, again, what I was going to mention is this next section is talking about radio theory. So if you don't know how a radio works, I suggest you get a book like this. This is for the AM only band. In this case, we're looking at approximately a 1 megahertz signal, and then we're down converting that to an audio frequency that we can actually hear. And it's that concept of down converting that we're going to be talking about. So I'll be using terms like oscillators, filters, and mixers. So if you're familiar with those terms, you shouldn't have any problem following along. I'll try to keep everything very simple. If you do a patent search for number 8073656B2, two inventors by the name of Peter Pawlowski and David Graff, who worked for Teledyne LeCroy, it came up with this scheme. I don't take any credit for this. What you're looking at here is a software simulator. I'm going to be using this to kind of explain this technique of downsampling that they came up with. I'm actually kind of surprised that this is a novel technique, because if you work with radio at all, a lot of what I'm going to show is going to be very familiar to you. In the top screen, what we have is a time display, and in the bottom screen, this is a frequency display. This is unitless, so you can consider this in units of Smiths. You can see we have one spur that's at the fundamental frequency of our sine wave. Let's just change this to a square wave, and you can see the different harmonics showing up. We'll go back to sine wave. Let's go ahead and change the frequency. You can see I'm increasing that, and you can see our spur is increasing in frequency as well. We can also modulate this waveform. Let's go ahead and add some modulation. And this is the second harmonic. Let's go ahead and we can increase that. You can see I have quite a bit of range for both of these. Let's just say our simulated oscilloscope has a maximum frequency of 500 Smiths. Let me just turn on our LO. Now this is our local oscillator, and this line represents the fastest that the scope can read. So it can read everything to the left of this, or lower frequencies, and everything to the right it can't read. So if I were to increase the frequency of this harmonic, once we get up into this range here, the scope could no longer read this. So the first thing that we need to do is separate out this high frequency from the low frequency. And we're going to do that with something called the diplexer. And a diplexer is nothing more than a high pass and a low pass filter combined into a single package. So it's a 3-terminal device. We display that in time domain. This will be our low frequency signal representing this spur, and this is our high frequency signal. Let's just zoom in on this a little bit. So again, here's our low frequency and here's our high. What we're going to do is we're going to take this local oscillator and we're going to mix that with a high frequency signal from the diplexer and generate this IF, or intermediate frequency. So that looks like this. So again, here's our diplexer low. You can see it's just a single spur at the low. And here's our diplexer high. And again, we're taking this LO and we're mixing it with this diplexer high. That's generating this IF frequency. You can see as I move this lower in frequency, I have another spur up here. So during this process of mixing, we're taking whatever this LO is and we're subtracting off this frequency, and that's giving us this spur, and we're also adding the two, which is giving us this spur over here. What we need to do now is basically remove all of the information that's in this upper band. So we're going to run this through a low pass filter. And now you can see we basically just have the one spur. Let's turn off the others. And here's our one spur that we're interested in. Now we've had to gain that up a little bit. Let's just have a look at that in time domain. And this is what it looks like. Now we have our two signals, and these both sit below the frequency that the scope was capable of measuring. So to be clear, again, we have two channels of the oscilloscope. One of them is being fed directly from the diplexer low frequency, and the other one's coming off of the diplexer's high frequency signal. It's been downsampled. So now let's pretend our scope has digitized both of these signals. The next step is to take and rederive our clock that we're using as the LO, but we're going to be doing that in software. So we know that we're running at 500 Smiths, so we're going to derive that same sine wave in software, and then we'll mix that with our downsampled signal. So that's going to look like this. And again, this is taking our LO and we're adding our signal and we're subtracting it. And that's giving us these two spurs. Now again, we're only interested in information that's above the LO. So what we're going to do is run this signal through a high pass filter. So now we just have the single spur. So let me just zoom out, and you can see now I have two spurs, one basically being our diplexer low and the other one being our rederived high frequency information. So now what we need to do is combine these two waveforms. So basically all we're going to do is sum these two together, and we end up with this waveform. Now if we look at the original waveform, you can see that the two are very similar. There's just a slight gain change between the two. So let's look at this in time domain. Again, this is our time domain high frequency information, and this is after we've recombined it. And you can see these are right on top of one another. So again, mathematically, all we've done is we've taken the high frequency information, we shifted it down into an area that the oscilloscope could measure. We measured it, and then mathematically we shifted it back up, and then we recombined it with our low frequency information to recreate the original signal. And you can see as I change the modulation, it tracks it perfectly. Now of course there is a limitation. Again, here's our LO at 500. We said that we could double it, and let's go ahead and take a look. We're going to increase the harmonic frequency just beyond double. Oh, and right there you can see it's gone to 0. So all that's happened here is that we've aliased this high frequency information. Let's just zoom into this a little bit. Again, right here is our high frequency information, and I'm increasing it, and bang, right here we're on the other side of that LO oscillator, and now this information is no longer going to be included. Now likewise, if we were to take that harmonic and push it down below the LO, of course now we have no information that's higher than our LO, so everything now is just being handled directly by the diplexer's low frequency filter. Let's change our modulation's wave shape from a sine wave to a square wave. And of course now we have all these high frequency spurs from the square wave. You can see these extend way beyond what the scope is capable of measuring. Those spurs will continue infinitely as long as it's a perfect square wave. Let's go ahead and increase our frequency. You can see the waveform is actually a sine wave that we're reproducing. And again, that's just a limitation because as we look at the harmonics of this, they're already beyond what the scope is capable of measuring. Again, to look at something like a square wave, we would need infinitely higher bandwidth, more than just double. Let's just look at it with a triangle wave. Right at the peaks here, it's not quite able to reproduce it, but it does a pretty decent job. So for this contest, again, the goal was to try to build a high frequency oscillator on a breadboard, and one of the rules was that it had to be sinusoidal. From that regard, we really don't have any low frequency information. So when we talk about our imaginary oscilloscope that we just went over, we really don't care about the diplexer because there's no need to separate the high frequency from the low frequency. There is no low frequency. So that simplifies the circuit. So essentially all we need is a local oscillator that's very fast, and in this case what I'm going to be using is this old Vantech Yig oscillator. So this will be our incoming signal. It goes into one leg of the splitter. Half of it goes out this port here. This is going to be used to drive the frequency counter. The other leg goes into the RF input of the mixer. Again, the mixer is going to add and subtract these two waveforms and combine them into this IF frequency, or intermediate frequency. That's going to run through this low pass filter, and then we have to re-amplify the signal to take up the losses of the mixer. That's what this box does here, and the output of this goes off to our oscilloscope. So again, let's say we had a 100 megahertz oscilloscope was all, and let's say our oscillator ran at 6050 megahertz. So what we do in that case is program the YIG for 6000, and then we take 6050 minus the 6000. That's going to give us a 50 megahertz signal, which would then get passed down into our 100 megahertz scope. So we could use that 100 megahertz scope to look at a very high frequency without any problem. The key here is that you have to know what the frequency is. Fortunately, in our case, we have a frequency counter hooked up to this, and that allows us to tune the YIG. I thought I'd mention that I actually broke my old record, and I don't remember which one of these arrangements it was. Maybe this one here, I think, maybe. You can see the nail polish on it. Well, I had ran a bunch of tests with this nail polish up at about 6 gigahertz, and I didn't see any problems. I also tried looking at it with the electrometer, basically covering up a circuit board with this, letting it cure, and I couldn't measure it with the electrometer. So what had ended up happening is I applied that to this coil to again give it some physical strength. You can see these are pretty flimsy, and of course the frequency went way down to something like maybe 4 gigahertz. And I came in the next morning after this had fully cured, and I think it got up to about 5 gig. I didn't take any pictures of that, no videos, nothing. You just have to take my word for it that I actually broke the old record. A friend of mine, Flipper, had picked up this white coax, so I made a couple of cables out of this. You can see how flimsy this is compared to even these blue cables I was using. The problem that I run into with the breadboard is the amount of strain that's placed on this connector from these stiffer cables. You can essentially tear this thing right off of the board. So what I've done to try to combat that, along with these cables, is I've got a couple of copper wires that make a loop around the coax and then tie it back to the breadboard, just basically trying to hold that stable. So I'd like to do now is hook up this down converter to our oscilloscope and then basically show you how this thing works in practice. And what I have here is a tripler. Now this has an upper limit of 8.1 gigahertz, so if we took the 2.4 gigahertz, multiply it by 3, that's going to give us an output of 7.2 gigahertz. So then I'll take the output of the tripler, I'll feed it through this high pass filter, and we'll use this as our test signal. As far as tuning the gain of this amplifier, what I did is I applied a signal to this whole arrangement using my signal hound. I kept the frequencies below 6 gigahertz so I could actually monitor them, and I checked the losses of the mixer and everything, and then I compensated for that with the amplifier. So basically what I was looking for is that the output here basically matches what I'm getting at the input signal here. So I've set our local oscillator to something that the signal hound is capable of reading, and again the signal hound's upper limit is 6 gigahertz, and you can see this is at 1.6 dBm. This is running through a 10 dB attenuator. All I'm looking for here is to make sure that we have enough signal strength to drive the mixer's LO. Now this is a signal that I'm deriving off of my Marconi RF generator. Now of course that signal generator is only good to 2.4 gigahertz. I'm feeding that signal through a tripler, and you can see our output signal is 14.78 dB. So these two signals now have been fed through the mixer and then through a low pass filter. You can see I'm generating a signal at 1.2 gigahertz, and it's a negative 20.84 dB down. So the next thing we need to do is amplify this signal, and then this next shot you can see I've pumped this up a little bit, and we're now at 14.81 dB, and again that's compared with our original signal at a negative 14.78 dBm. We've got our Marconi generator. You can see it's outputting 2.2 gigahertz. Now this generator and these two counters are attached to a GPS receiver that's driving the reference clock. So the output of this RF generator comes down to our tripler and again goes through our high pass filter, and that goes into the input of our splitter, and the one side of the splitter, which is this cable here, going into our microwave counter. So if we take our 2.2 gigahertz times 3, that's 6.6 gigahertz. And again, because it is all tied to the GPS, that's why these two will track. Again, the other leg from our splitter feeds into the mixer. Our oscillator is currently set for roughly 6 gigahertz. So essentially we're taking the 6.6 gigahertz, we're going to subtract off the 6, and that is going to give us this 600 megahertz here. You can see this is still drifting a little bit. It's because we just turned it on, It'll take a little while for that yig to stabilize. What I'm going to do is adjust this thing up 100 megahertz. So we'll be taking 2.3 times 3, and you can see that gives us 6.9. And again, so the yig is running at 6 gigahertz. So the 6.9 minus the 6 will give us 900 megahertz. Again, this is the upper limit of this Marconi generator, is 2.4 gigahertz. Again, 2.4 times 3 gives us 7.2. And again, 7.2 minus the 6 gives us 1.2 gigahertz. So that's basically how the math works. What we can do now is connect this up to our oscilloscope, and I can show you what the output of this looks like. You can see our output cable now is feeding into channel 2 of the oscilloscope, and we can see the scope's displaying roughly 1.2. You can see we are running in wrist mode. It's at 100 gigasamples per second. But again, this oscilloscope is only rated for 600 megahertz, so that signal is fairly attenuated. Let me just show you what happens if we slow down our RF generator. So this is at 2.3 gigahertz, and this is 2.2 gigahertz. So again, 2.2 gigahertz multiplied by 3 is 6.6. So take the 6.6 minus the 6 gigahertz of the yig. Again, that gets us into 600 megahertz. Very close now to what the scope is capable of reading on the upper end, and you can see it is displaying 600 megahertz. So I'd recently shown some pictures where I had homemade some Lutz wire, and this oscillator has that on there. Let's just go ahead and hook that up. This is currently running at 1.13 or so gigahertz. So again, we would add that to the 6 gigahertz of the yig. So this particular oscillator is running at roughly 7.1 gigahertz. And we can verify that by looking at our counter. And you can see it's 7.121. And again, it's bouncing around a little bit, but 7.12-ish. But again, we're at double the frequency rating for that oscilloscope, so we're pushing her pretty hard. But I spent some time looking through DigiKey. I found some nice transistors out there that would blow the doors off of this thing. We could easily look at maybe doubling this frequency. Of course, that's really up to could you actually build it and make it work. This particular oscillator is pretty touchy. If you run your fingers or bend anything down in here, that's going to have a pretty dramatic effect on this oscillator. Hopefully this video gives you some idea how you can use a lower frequency oscilloscope to look at some fairly fast waveforms. And again, to be clear, there isn't a whole lot invested here, and you can still find old yigs used. They're fairly inexpensive. I've got some brick oscillators. You can see this one was made by Frequency West. It says a maximum output frequency of 5.3 gigahertz. The problem with using this oscillator for this particular experiment is the output amplitude of this isn't high enough to drive the mixer's low input, so this would have to be amplified. So I had this yig in my stash. You can run it at a lot higher frequency than this. It just makes for a more flexible design. Using this with the LeCroy 8500, just the way it sits, it's 6 gigahertz. You add the 5 gigahertz to that, and essentially we've got an 11 gigahertz scope. The mixer that I'm using is good for that frequency range. That's not a problem. So if I decided to build a faster oscillator, I definitely could use this setup to show you the output wave shape. I think that's going to be it. I hope you enjoyed the video. Hopefully everybody's healthy and you're starting to enjoy some of the sunny weather that we're having. So all for now. Later.